recording starts. Okay, just starting out. All right, so let's continue. It's been a while since the last lecture. We started to talk about logistic regression. We want to describe this new learning model. So far, we have seen the data set, which is the same as before. We have seen the hypothesis set, and we have seen this is the hypothesis, right? It has this sigmoid function that looks like this. And then we also saw that there is a loss function. The loss function is what we call the log loss function, right? So last time we looked at some numerical examples, see, well, maybe it makes sense. But today we're going to focus on the log loss function for an entire hour, okay? So that we really, hopefully, understand a bit more about this loss function. So the question is, why do we use this log loss function? So En, the loss or the error for the particular sample point is of this form. Let's just take the log of your predicted probability for that point, right? Just like that. Remember here, Yn is a true label, right? So you just plug in that probability and then take the negative log, and that's what we say it is the error function for that particular data point. Yeah. Again, last time we saw maybe at least for some extreme cases, it makes sense, right? That if your prediction is a very high probability, very confident that it is say +1, but then the real label is -1, then your loss will be very high. Yeah. Whereas there's a good match between your confidence and the true label, then your loss will be small. Yeah, we'll saw some examples there. But let's again write this in a bit more detail. So this one turns out to be, we showed last time that when you substitute the sigmoid function into this p, that's what we get. Right? It's easy derivation. So today we're going to talk about a bit deeper mathematical reasoning behind this function. But before we go there, let's first make a comparison with linear classification. Okay, so the hope is to show that this loss function is better than the loss function for the linear classification in some general sense. Benefit over linear classification. In this example, again, two-dimensional data points. It is in the form that we have kind of seen before. Okay. Suppose I have a data point here, which is a plus. I have a data point there, which is a minus. Okay, only two data points. So therefore, n equal to 2 in my data set. Okay, so the first data point is assigns the numbers. This is not augmented. So the coordinate is 0.01 and then 10. And then the label is +1. Second point, of course, is the anti-symmetrical point. And it turns out that the label, this one is minus. Okay, this is the data point. These are data points that are given to you. Okay, you have no choice of the method. That's just your training data set. Now, we have done this before. For the linear classification, let's compare two different boundaries. Yeah, we can have one that looks like this. So this is L1. L1. Okay. So the functional form is x1 equal to 0. Okay, so this is a function, right? This is not just to say that the first attribute is 0. This is a function. So given this function, what is the equivalent way of writing this W1? What is it? Someone can tell me? what is corresponding W1? Let's say we use the augmented form now. The augmented form of the coefficient. Yeah. 0.
If augmented, it's then 1, 0, 1.
1, 1, 0, 1, really?
Wait, the first one, W0 is always 1, right?
No. X0 is always 1. Remember, be careful now. Yeah, X0 is always 1. Yeah. So how do we come up with this? Well, what you write is this form is the same as saying we have a 0 multiplying x0, and then we have a 1 multiplying x1, and then we have a 0 multiplying x2, right? This is equal to 0. Yeah? That's what the line means, right? So therefore, corresponding W would be 0, 1, 0. Yeah? Now, for the second line, let's consider the horizontal one right on the x-axis. Yeah? L2 is x2 equals 0, of course, right? So now W2 should be easy now. What is it equal to? I won't write this. If you want to exercise, you can write it yourself. But clearly, this is going to be 0, 0, 1, right? Okay. That's the second line. Yeah. And for linear classification, we discussed this before. Which line do you think would be better? Yeah. Which line is better? Well, remember, linear classification, we're just counting the number of errors, right? So this is indicator function 1, yeah, yn, 1 of yn not equal to the predicted label, which is this inner product, right? This is our error function for the linear classification, yeah, for this particular point. So which line is better with respect to this error? They are the same. They are the same, yeah. Both of them make 0 errors. So E in W1 is equal to E in W2 is equal to 0. Okay. So for this linear classification error function, okay. But as we discussed before, our well-trained brain, looking at these two lines, intuitively, we should say which line is better. Which line, the red one or the blue one? Yeah, blue one. Why? Yeah. The blue line, we have intuitively say that, well, this line separates those points better. Yeah, those points are further away from the boundary, right? So in case there is some kind of error when in the real world, when we test this boundary with some noise in our data points, we're less likely to make mistakes, right? Yeah, we have more room to play. Okay, so intuitively we know that in reality the blue line should be better, but then if you just do linear classification, you cannot tell. Yeah, both of them are as good as one another. Now, the claim is that for logistic regression, that error function can tell, the log loss function can tell the difference between these two cases. Okay, so let's see the numbers. So let me write E in, and just the subscript is a bit messy, so I use color to represent different lines, right? Remember W1, W2 represent the two different lines, right? So the first one, E in is what? It's a log loss, right? So half average loss. So there's a half of the log, which is what do we have? It's here, right? Second line there, just substitute the 2 points. We only have 2 points, 2 exams, n equals 1, n equals 2. So substitute in there log of 1 plus E minus W1 transpose x1. Here x1 is the first data point. W1 is first line. Yeah? Those two subscripts ones are different things. Be careful. Let's see. This one, the second point, because the y-end is negative, so we have positive W1 transpose x2, right? For the second point, y2 is negative, so negative, negative cancel out. Yeah, everyone okay with how we get to this point? Why there's a sign change between this term and that term? Everyone okay? Yeah, because we have to account for the yn, right? The true label. Don't forget. So once you have this, then you just substitute into the numbers. Yeah. So 1 plus e minus 0101, and then log 1 plus e. If you multiply them out, for x2, it turns out still to be minus 001. Okay. Okay. Be careful. There's no typo here. Okay. Hopefully no. Yeah. Above the first line, there's a sign change for the two different terms, but then in the second line, both of them have negative in front, okay? Because now you have x2 instead of x1, yeah? Be very careful about these signs. A little error with the signs, you get maybe 0 in your exams, right? So this turns out to be approximately 0.693, okay? So that's the error, yeah? The error amount for the first line, the red line. So likewise, we can do the same thing for the blue line. Yeah. And again, substituting the formula, log 1 plus e minus W2 transpose 1. Transpose x2. Yeah, again here, W2 represents the second line. Yeah, x2 represents the second data point. They're totally different things, right? That those two subscript 2s are totally different things. Be very careful. That's why I want to use colors to separate them. And then if it's substituting the numbers, we already know the W2 and we also know x1, x2, then this is 1 plus e. Turns out to be huge, right? Now you pick up the other dimension, the second dimension. So the 10 shows up here, or minus 10, like that. Okay? And as you can imagine, it's 10 e to the minus 10, right? It's a very, very small number, yeah? Even after the log. Minus 5. Okay? So the blue line's error is much smaller than the red line. Yeah, much, much smaller. And therefore, we know that we should favor the blue line, L2. Yeah? L2 is preferred. And this is as expected. Yeah? As expected by our well-trained brain. Yeah? That we know it should be preferred because there's more space between the boundary and the data points. And that's achieved only by logistic regression. Yeah, linear classification cannot do it. Everyone okay with this for now? Yeah, this analysis here, this kind of how we get these numbers. Okay, the details are important, right? This is a math course. Details matter. Yeah, you have to be able to come up with the same answer. You know, anytime that you miss a little sign here and there, the numbers were totally wrong, right? So we cannot allow any single minor mistake in math. If everyone is okay with this, then let's talk about something that might be a bit surprising to you. Yes, okay.
For the 0, for example, for the 0.693.
Mm-hmm.
So is that like we can understand it as a probability of what?
Not quite. It's the log of a probability. So unfortunately, we don't really have a lot of physical interpretation for that log of a probability. Okay. Now we're going to talk about the why minimizing this makes sense later. Okay, in maybe after 5 minutes. Yeah, but we don't have any measurement for what this number means. In fact, the other day someone asked me, what does this number mean compared with that number? how much is this smaller than that one? Unfortunately, we don't have a physical meaning for them. Yeah, we can only say this one is better than the other one. That's really to the extent.
And the reason is because the one L2 is smaller than
Yeah, because it's small. The area is smaller, right? We always want our area to be smaller. Yeah, and also what we show is that it does make sense. The smaller area corresponds to a line that is better. Yeah, farther away from the points. Yeah, what do we know for now? Okay. Now the reason that this is very hard to interpret is the next thing that's a bit surprising. Okay. Suppose we consider another line. W2. You can call it W3, but it turns out that W3, I can call it W2. How about this line? If these are the coefficients for my line, what is this line? And why do I write it as W2? I don't write it as W3. Yes? Yeah, multiply. But where's the line? If I have to draw this line, what does it look like? Same line, yeah. The same blue line. Okay? In fact, you know what? Because it's the same, let me change it to blue. Make it more striking. Huh? It is the same line, right? Yeah? Even if I can scale W in any way, I still get the same line. Yeah? Should be clear by now. Yeah, right? From, I don't know, elementary school math. But what happens to the error? If you substitute these numbers into this formula for W2, this minus 10 becomes minus 1,000, right? Because multiply 100 times, right? Previously it was 1, now it's 100. So minus 10 becomes minus 1,000 if you do the calculation. This number will be much smaller than the previous one. But it is the same line, right? Now we have a much smaller number for the error. So that means what? These kind of error measurements are not unique for the same line even. Okay? I can arbitrarily scale it any way you want. Okay? And that's why these numbers, they don't really have a very precise physical meaning. They don't. You can only compare them. Say I fix the norm of the W to be 1 on both cases and then compare them. Okay? So that's a very important point to note. But the loss, E in, now is much lower. Okay? So because of this non-unique measurement of error, the plain version of logistic regression would not work in practice. Okay? Either we have to say we set a constraint, the norm of W is always equal to 1. Okay? But better yet, we do a regularization, which we have seen for linear regression already. Right? So logistic regression typically requires regularization. Yeah, so as we have seen before, we just regularize on the size of W. Okay. This way of doing it, that way you can just minimize this whole thing together without any constraints. Okay. The other approach is to say I fix the norm of W to be 1, but then now when you optimize, you have a constraint optimization, which is usually harder to do. Okay. All right, everyone okay so far? Yeah, everyone surviving? Today the first hour is a bit dense, and then the second hour is more relaxing. Okay. Now let's go to the a bit more advanced mathematical reasoning behind this log loss function. Okay. So far we only have numerical demonstration to show that it makes sense, right? Kind of fits our intuition. But how about a bit more rigorous math? Yeah? So turns out that there are two different ways to understand this log loss function. One, it turns out that when we minimize the log loss, we actually maximize the likelihood And then the second one says that if we minimize the log loss, we minimize what's called the cross entropy. Yeah. So we'll get to these 2 points. First, maximum likelihood interpretation. So again, suppose we have the data set that's given to us. There are m points. We have no choice out of matter. We're just given these data points, right? And the data points are generated from some target function that could be random. Now let's consider this probability of actually observing such a data set. Okay, we're given this data set, but then we say, well, before they're given to me, if I have to guess what is the most likely data set that we will see, yeah, then we'll be considered this joint probability, which is P y1 yn given x1 xn, like that. This conditional probability. Yeah, so this is, of course, this is by definition is the probability that the first label in our data set, yeah, is y1, and the second label is y2, and so on and so forth, right? Given that the first data point, first data example is x1, and second example is x2, and so on and so forth, right? Yeah, that's just the shorthand for writing out this bigger kind of almost English form, right? So another way to write this in a more quasi-English, yeah, is the likelihood of observing this particular configuration for a data set. Yeah? Observing the labels y1, yn, given data point x1 xl. Yeah, that's the kind of the English way of expressing the same idea. So again, this is the question: is, you know, if I haven't gotten the data set yet, what would be the likelihood? What is the probability I would get this data set? Okay. But now that I'm given this data set, so what I need to do is to figure out a W function that can allow me to generate this data set with the highest likelihood. That's the whole idea of maximum likelihood. Okay. But let's break this down slowly. So first of all, this is a joint probability, right? So if we can assume that these data points are independent of each other and they're identically distributed, then I can write this as a product of those conditional probabilities. And this is the usual assumption anyways. When we're given the training data points, we assume that they are identically distributed and independently generated. So P yn given xn. So here this is because we have the ID assumption. ID data samples, or examples. ID stands for independent and identically distributed. Yeah? Independent and identically distributed. You have seen this in your probability course. Any questions? Independent and identically distributed. Now, of course, this product, I can rewrite the probability inside by our hypothesis. That this is simply this, right? We guess that it is generated by this probability which is determined by the W that we choose, right? Yeah, that's our hypothesis. Yeah. Okay. So we have opportunity here now to choose a W so that this probability is maximized. In other words, the likelihood of seeing what we have been given is maximum. In that case, then we will say this W is a good choice for that W, right? Yeah, this W fits what we generally expect because we are given this data set. Yeah, if this W really generates the data set with high probability, then this probably is a good W. Make sense? Yeah. So that's our goal. Yeah, we want to find a W, well, in the augmented form, yeah, that maximizes this probability. Yeah, P y1 yn given x1 xl. Yeah. So that means we want to maximize to maximize this product there, right? This product P hat, I can first of all put a constant in front, doesn't hurt. And then we'll take a log of that product. Doesn't hurt either. The log function is a monotonic function, right? I just copy this directly without any change. Just adding the log in front and a constant in front. Yeah. This is okay, right? Same as before. But what is this equal to, though? Why do I want to put a log like that? Well, because log of the product equals to sum of the logs, yeah. So now I get sum of the logs. Like that. Does it look familiar now? Maximizing this, but we have a negative log function, right? But so maximizing this is the same as minimizing the negative. Yeah. So this is the same as minimizing 1 over this and sum 1 to n negative log. Yeah. And once we write this form, I hope you recognize that the inside is just our logs function. Right? So it's just simply en w. Yeah, that's exactly what we have before. Logs function. This is our area measurement for w, for the line that we have chosen. And of course, this, if you write almost this vector is en. Oh, oops. Yeah. W. Yeah. For any line w that you choose, you have a loss function, right? You can calculate the error amount. Yeah. Turns out that if we minimize this error amount, we are maximizing the probability that we see the data point that we are given. Okay? So the W that maximizes that probability clearly is the best one that we can have, yeah, given the data set that we have. Yeah? Makes sense, right? This is so this is the maximum likelihood approach. Okay? Those of you who have taken, say, probabilistic reasoning, yeah, ECE 368, you have seen a lot of this maximum likelihood estimation already. Yeah? But no worries, you haven't taken the course. Now you see it. Yeah? It's a very simple idea. Yeah? Just maximize this likelihood of seeing something that you're given. Yeah? And turns out that W is the optimal estimator that maximizes the likelihood. Yeah. Yes? Okay, what is it? No, remember this P hat is this guy, right? Our sigmoid function. This is our model, our hypothesis, yeah? For now, it's the sigmoid function for logistic regression. Later, when you go into more complicated learning methods such as neural network, this thing could be something else as well, okay? But in general, the loss function is to taking the negative log of the probability. Yeah, but so happened here that we estimate the probability using a sigmoid function. Okay. Yes. Okay. Where? Okay. How the minus sign come in? Yeah. To maximize something is the same as minimizing. It's opposite. Yeah. Okay. All right, so this is the maximum likelihood interpretation. Yes?
Where does the 1 over n come from?
Oh, 1 over n is just because the definition of E in has to be the average, right? So we want to include 1 over n. And previously, when we include 1 over n here, does not change anything because multiplying 1 over n, 1 over n is a positive number. Multiplying constant does not change the maximization, right? Yeah. All right. So now let's talk about the second interpretation of the log loss function. This log loss function is so important. That's why we want to spend a bit more time on this, going through the theory behind the log loss function. All right. So the second one is so-called cross entropy interpretation. So of course, the idea of entropy is extremely important, both in physics and in mathematics, especially in information theory. Yeah. How many of you have already heard of the term entropy? Yeah. Okay. Few of you. Very good. Yeah. So cross entropy is a bit different from the regular entropy. Okay. Cross entropy measures the distance between two different things. Yeah. So more precisely, it measures the distance between two different distributions, probability distributions. Okay. So definition. Yeah. Suppose we have two different distributions, P and Q. Two probability distributions. Let's say they're all the same sample space of x1, xm. This is different from the features of our data point. Okay, this is just a general symbol for the values that random variable can take. Okay. Yeah. So just as an example, just for those of you who might not be very comfortable with your probability, do you remember the Poisson random variable? Say with the mean value alpha. Yeah. What is the sample space? Sample space means what kind of value the random variable can take, right? The universe of the random variable. What are the values that the Poisson random variable can take? Does it? Nobody remembers the Poisson random variable? Dr. Poisson? Poisson was one of my advisors. Go back how many generations, I don't know, but maybe 20 generations. So Poisson distribution, the sample space, it can only be non-negative integers, right? It's just how many things, how many, say, dots are inside a space, or how many objects are there inside a box. Yeah. So the sample space is 0, 1, 2 to infinity. Yeah? That's the sample space. But more importantly, what is the distribution of a Poisson random variable, P of x? Yes? Oh, Q. Yeah, Q. Okay. So anyone remembers the distribution of a Poisson random variable? Probability is a prerequisite course, right? So I expect you guys better than this. Come on. Yes? Okay. Yeah. Okay. Yeah. There's a lambda there, but the lambda is the mean value of the Poisson random variable. And here we use alpha for the mean, another common form. So it will be alpha to the x power. Yeah. So alpha to the x power divided by x and then e to the minus alpha, right? That's the distribution of a Poisson random variable. It's a function in x, right? The function in the values that the random variable can take. Just basically, this is the probability that the random variable will take this x value. Yeah, it can be 0 or 1 or 2 and so on. The probability that it takes one of these numbers is given by this formula. Yeah, that's what we mean by distribution. Right? Now, then once we have two distributions, so two different kinds of random variables, and we want to have a way to measure how different these two random variables are. Okay, how different and how similar they are. Okay, then we have to have some kind of a distance, kind of a distance between the two random variables. Yeah, and that one measurement is called the cross entropy. Yeah, okay, so let's define it properly. Cross entropy between P and Q basically is you can think of it as a measurement of distance. Well, is we use the symbol CE for it. Yeah, CE between P and Q, like that. Cross entropy. Turns out it has this funny-looking form, summing out all possible values the random variable can take, and then the probability it will take that particular value, and then times the log of Q of xi, like that. Okay. Have this funny-looking form. Okay. For now, we don't have to worry about why it has this funny-looking form, right? It is what it is. Okay. It basically measures the distance between two different distributions. Yes.
So P and Q is a point?
No, P and Q they're distributions. The P of x is remember the Poisson distribution, right? It's a function.
Q is also that.
Q is also a distribution. So it's a function in x. Yeah, both of them are functions in x's. We want to compare these two functions basically, how far away they are from each other. Yeah. Okay. And if you're very comfortable with probably you should see that this is actually an expectation of something, right? It's a weighted sum with the weights being probability. Yeah, it's the expectation of log Q. Expectation with respect to P. But that is not important. Yeah, we just know that there is this formula. That's all. Yes.
By distance, you mean distance between each of the points?
No. This is a special way of defining a distance of two random variables.
Yeah. Is it like covariance?
No, very different from those things. This is just what it is, cross entropy. Okay. Yeah. So cross entropy turns out to be a very important concept in machine learning. Shows up all the time because you always want to measure the distribution of the true data and then your estimated distribution for those data points. And then you say, how good is your estimation? Then you compare them, right? Okay. So you always see this so-called cross entropy loss function when you do neural network training, for example. Now, now we have defined cross entropy. It is used to measure two different distributions. Now I want to make a claim that for logistic regression, we have a true distribution for the labels that we have in our data set, and then we have an estimated distribution for those labels. And then I want to compare these two, and that turns out to be our log loss function. Okay? So let's see. For the nth example, consider the distribution as follows. This is I write the true distribution first. P n. I want to write probability that yn is +1. And then Pn, this is a vector, right? A distribution is a function, so it's a vector. Yeah? It's a function for discrete values, so it's also a vector. So we only have two different values. for this label, right? Either +1 or -1. So this distribution also only has dimension 2, yeah? Two possible probabilities, right? They of course have to sum to 1 always, yeah? These two have to sum to 1. So this is the distribution of true labels, Yn, yeah? True label, Yn. But what is this equal to, though? Depends, right? We're already given those data points. We already know Yn. Yn actually is deterministic right now, yeah? So, but we have to force ourselves to write this as a distribution so that we can use the cross entropy. So there are only two cases: if Yn is +1, or if Yn that we have is -1. Yeah. In these two cases, what is the distribution then? Well, this is probability is +1, right? If I already know this +1, then the probability is 1, right? Well, for sure it's 1. And then the probability is -1 is 0, right? So therefore, for this kind of deterministic numbers, our probability always, for one value is 1, the other values are 0, yeah? Because this is deterministic. There's nothing random about them anymore. 0, 1 here, right? Okay? Everyone okay with this idea? So even deterministic numbers have a probability distribution, yeah? Only that the probability distribution is a very extreme case. That is all concentrated at one value. That's all, right? Okay? So 1, 0, and 0, 1. Everyone okay? Now, there are two lines here. I can, again, combine them into a single line. Turns out we can do that. I just write 1. The indicator function here is equal to +1. And then 1. Yn is equal to -1. It's the same as the two lines above, right? Okay? I hope everyone is convinced that this is the same as before. Yeah? Well, 1 here, again, is the indicator function. By the way, textbook's way of writing indicator function is a bit different. It's a kind of a double bracket. Yeah, just watch out for that. This is more conventional, more common. Okay. So now we have the true distribution for the labels that we have for this label that we have for this particular point. Now, what is our estimated distribution for the labels for this point? Okay. Let's call it Qn, that we'll compare with Pn later. Qn is our estimation, right? So let this equal to the distribution for our line, that this is 1 given xl, right? This probability that it is 1. And then we also have an estimate for the probability that it is -1 given this xl, right? Yeah? So this is our estimate for the distribution of Yn given xl. Yeah? Okay. So we already have a true one and then the estimated one. We want to compare how close they are. Yeah? Of course, the closer the better, right? Closer the better. So what is the closeness between these two? Pn, Qn. Just go back to the definition of the cross entropy. It is, of course, the right here, right? Just negative. We use a negative in front because the Q is a distribution, so Q is always less than 1, right? Q is less than 1, therefore the log is always negative. That's why you put the negative sign in front to cancel out that one, yeah? So it makes sense, right? Even though it looks a bit strange, why I measure when the distance is negative, you know, but turns out at the end it gives you positive, yeah? So it's negative, and it's a sum. We only have two cases, either +1 or -1. So this is the 1, this is the Pn, the first term of Pn, multiplying the log of the first term of Qn, which is this is 1 xl. I have a mistake in my notes. -1. And then plus 1, yn negative 1, and log pw negative 1 xn. Like that, right? Just to substitute him into that formula, that's all. Yeah. Yeah? Well, if you see this, what do you observe? Well, this is an indicator function, right? Only one of them will be active at any point. Yeah? For any value, only one of them will be active. So we can actually do our trick again to combine these two together into a single one, just using yn. Right? So this is actually minus log of pw hat yn given xl. Yeah? Right? Yes? I don't have to, because this is, one is negative 1, this one is, oh, what did I do? No, that's fine, right? This is the same as this one, right? Because when this is negative 1, this yn becomes negative 1. Yeah? And then this one say, this is true only if yn is plus 1. In that case, this yn goes to plus 1. So these two are the same thing. Yeah? They're the same thing. Okay. So again, yn can take only two possible choice values, either plus 1 or minus 1. Yeah? Either case, this equation works. Right? Either case, this is correct. Therefore, they are just the same. Okay? And of course, this is our measurement of the goodness of W, right? The loss function for that particular point. So it turns out that our loss function actually is a cross entropy between the true distribution and the estimated distribution. And therefore, it makes sense to minimize it. Yeah? Makes sense to minimize this error. Yes?
Doesn't make sense how you went from the first line to second line.
Let's go from second line to first line. That's easier. There are only two possible cases. Yn is plus 1 or minus 1. So basically, when you go from second line to the first one, we just break this into two possible cases. Yn is plus 1 or minus 1. Yeah, there are two terms, right? Yeah, that's easy to see maybe. Yeah. Okay, so that means that, let's see what I want to say. If we want to minimize the E in, it's the same as saying that we want to minimize the average of these values, right? So the average cross entropy, and therefore the average distance, quote-unquote distance. Yeah, it's not a real distance, but it's some measurement of distance between Pn and Qn. Yeah. Yeah, over the set of elms, over the set of data points, which clearly makes sense to us. Yeah, that's what we're going to do. So, yes.
Okay, this is kind of unrelated, but does that mean like the sine function is also like a type of probability distribution?
The sine function SIGN, the sine?
The one that goes like
Yeah. It is not a probability distribution because it's minus 1, 1, right? It's negative sign. It's negative. Yeah. Yes?
In the cross entropy function, does it matter the order of P and Q?
It does matter. Yeah, that's a very good point. The cross entropy turns out it's not symmetrical. So cross entropy of QP is different from cross entropy of PQ. Okay? Yeah. Here we have to choose to put P first, because if you put P in back, when you take the log, what happens? Because you have 1 and 0, right? The log of 1 is always 0, log of 0 is always minus infinity. So that would not work. Yeah. So we have to do cross entropy PQ in this case. So therefore, I hope that by now everyone is convinced that for logistic regression, this log loss function is a good measure to use. Now what remains is what is our algorithm to minimize it, yeah? So how to minimize E in. Okay, and that would be something that we discuss in 10 minutes after we take a break, yeah? So, see you in a bit. All right, let's resume. So now our question is, how do we minimize this E in, knowing that this E in is a really important quantity that we really want to minimize, both numerically that we have seen and also mathematically, that this E in is an important quantity. Unfortunately, this form of E in, also sometimes called the cross-entropy loss, as I mentioned, this is a lot more general than just logistic regression. Okay? So it's this is a loss function that is widely used in machine learning. Unfortunately, this cross-entropy loss function does not have a closed form for its minimization, unlike the linear regression. In linear regression, we have a very nice form. Take the pseudo-inverse and all that, we can calculate it very quickly. Yeah, but unfortunately, to minimize E in here for logistic regression, we cannot, and we don't have an analytical way to minimize it. So we have to go back to a numerical method, iteratively reduce its value, and that common method is called gradient descent. So I think if you have seen any machine learning at all, you will have heard of gradient descent. Right? It's one of the most commonly used optimization algorithms. So what is it? Yeah. So we use it to minimize a differentiable function so that we can have a gradient. Right? If it's not differentiable, then it's things like you don't even have a gradient. Then we have to go use some other methods. So a function that maps from Rn to R. Yeah. So here, just we use a common notation of n here. It indicates the dimension of this function. Okay, it's different from our nth sample point at n. Yeah? Different n. So we want to minimize this function over the n-dimensional space. Yeah? We have a choice of a point in n-dimensional space to minimize this function. How do we do it? And clearly, this is an unconstrained optimization. Yeah? So it's a lot easier than constrained. So for now, we only discuss the unconstrained version of the gradient descent. Yeah? And one example that, of course, motivating this study is that we want to minimize E in of logistic regression, so which is the cross-entropy loss, or the log loss, that has this form, E minus Yn, like that. Yeah, that's the question we want to ask. But throughout today, we just use a general notation of f in an n-dimensional space to discuss this gradient descent, okay? So forget about machine learning for now, for a second. Just for this hour, we'll just focus on this pure mathematical form and see how we can minimize that function. Yeah. So it is, as I mentioned, it's a gradient descent is a numerical method. Yeah? It's not analytical. We're going to derive the form of gradient descent. Yeah? We want to properly understand why we do what we do. Yeah? Even though you might have seen it already in various courses, you might have used it already. So let's really go a bit deeper to ask why we do it. Just for the purpose of illustration, let's look at the case of n equals to 1. So in the one-dimensional case. So therefore, x is in R, right? In that case, we don't have a vector x, just single x. And then we know that we can take the derivative of this function, right? That is df dx of x like that, right? Yeah. You can draw this x, and then let's say the function looks like this, like that, f of x. Yeah, this one-dimensional function. And we know that, well, usually we assume that this is convex. So in other words, this is a shape of a bowl, right? A cup of bowl, whatever. Yeah. We assume for now fx is convex. But for now, later we're going to talk about what happens when it is not convex, which is very often the case. If it's convex, again, with our well-trained brain, where's the optimal? Where's the minimum? Right at the bottom here, right? So this point is the optimal point. And we know that the optimal point, let's call it x star. What is the gradient, or what is the derivative, or the slope of the tangent line? Many names for this same thing, right? So if x is equal to x star, yeah, f prime of x, of course, equal to 0. Yeah? Okay. What if x is on the right-hand side of x star? Again, this is a convex function, right? F prime of x is positive, yeah, greater than 0. And likewise, if it's on the left, this f prime is less than 0. So just one example point here. This is your x. Yeah. Then the slope of this line is the derivative, right? Yeah. So when it is on the right-hand side and the derivative is greater than 0, what does that mean? That means if you increase x, the function value will increase, right? That's what it means to have a slope that's positive, yeah? Or the derivative is positive, right? So fx increases with respect to x, yeah? And of course here it decreases. If it's on the left-hand side, then it decreases with respect to x. Okay, so and that gives you a clear way to write a code or design an algorithm to optimize this function, right? To find this optimal point, no matter where you are right now. You start from whatever. You check the derivative. If the derivative is greater than 0, then you'll know that you're on the right-hand side of the optimal. Then you go to the left one step, yeah. And then if it turns out that the gradient or the derivative is negative, then you know that you're on the left-hand side of the optimal. Then you go to the right. You go in the opposite direction of the derivative, yeah, opposite direction of that value of the derivative. So suppose you are here right now. Then you say, okay, now I know I'm on the right-hand side, so I go left-hand side one step. Yeah, maybe I end up here. Yeah, here clearly the derivative is still positive, so I go another negative step to over here and so on. Yeah, and so on and so forth. Yeah, once you get to the other side, then you say, okay, now I'm negative. I have to jump back to the other way. Yeah, okay. The hope is that will eventually converge to somewhere near the optimal point. Yeah, that's the whole idea of gradient descent. But in the one-dimensional space, it's a lot easier to see what it is doing. Okay? So, well, let's write it down. So we initialize x equal to x0. And then if it turns out that f prime is approximately 0, then you can stop. Not stop. And if this, make sure that you have included all cases, of course. Yeah? Then you go a bit to the left. If it's greater than 0, then you go a bit to the left. So you subtract an epsilon, yeah? Where epsilon is something that's positive. And if f prime is less than 0, then you go a little bit to the right. Yeah? So plus epsilon, right? Yeah? That's how you express the whole idea. A very simple idea, but sometimes I have to write it out properly, correctly. Is not exactly easy. And now you can go to step 2. Yeah, you can check whether the gradient is small enough. Yeah. And well, of course, you all know this epsilon is called the step size. Yeah. Just how long you go in one step. Yeah. The size of step. And what happens? Of course, you have a choice how big the step size is. Yeah. What happens to a large step size, and what happens if you use a smaller step size? What are the differences? Yeah.
Like if it's too large, you
Mm-hmm.
can go out of the bound and just.
Yeah, you just keep ping-ponging around the optimal. You're far away from the optimal. Yeah. But then, yeah.
So it takes longer to train.
Yeah. If you use a small step, of course, every time you move a little bit, then who knows how long you get to the optimal point, because you don't know what the optimal point is in general. If you knew ahead of time, you wouldn't be doing this, right? So you don't know how far away it is from you. If you use a if you're very, very cautious, then, well, it takes forever to get there, right? So both of them have problems, right? The large epsilon can give you a less accurate result. A small epsilon potentially give you a small progress, yeah? Potentially lead to very long runtime of the algorithm. The solution is erasing. It's a better way, yeah? Average? No, you don't know how big, how small it should be, right? Change the size over time, okay? Yeah, but how do you change the size? Make them bigger, or make them smaller? Proportional gradient, okay, that's a very, very good thought, okay? But that's a bit too much for us for now, okay? We'll talk about it later in the high dimensional space, okay? We'll get to that point. Okay? For now, all we need to say is that we want to change it over time, but then the question is, do you want it to be bigger and bigger, or do you want it to be smaller and smaller over time? Which case is better? Why is that? And then, so why is it good to have a smaller step size when you get closer to the optimal point?
So you get closer to the optimal point instead of like going bigger and further.
Yeah. As you get closer to the optimal point, you want to be more cautious. Yeah, you want to be accurate at the time, right? But at the very beginning, when you're far away from the optimal point, what you want is to have a big step so that you can get to the optimal point faster. Okay, so that's the general principle. So we're going to use epsilon t, where t is the iteration number. Yeah, and one common example for this is epsilon t is equal to 1 over t. So it naturally decreases as t increases. Okay? Yeah. Again, when t is small at the beginning, you have a bigger step. Yeah? And then as t increases, now you know that you're getting closer and closer to the optimal point. You're very cautious. You use a smaller and smaller step size. Eventually, this thing converges to 0, right? So you can converge to the optimal point exactly. Yeah? Asymptotically, you get to that optimal point. Yeah? In fact, if you use this step size rule, you always converge to the optimal point for a convex function. Most probably strictly convex function, but don't worry about that. So now this is for one-dimensional case. Yeah, very easy for us to see. I'm sure should be very simple to everyone, right? Kind of high school stuff, if not elementary school stuff. So what about the general DM? Yeah, when you have high dimensional space, that's a bit more messy, right? General M. Okay. So, but we use a similar idea, right? Given the current location, we want to update it. The question is, where should we go as the next step? What should be the next step? Let's say. Now, in a high-dimensional space, we are more than just left or right, right? We can go many, many possible directions in a circle or in a sphere, in fact, yeah? Hypersphere. Yeah? For the same step size. There are so many different directions. How do you choose the right direction to go? That's the question, right? Okay. But let's write down this idea first. So we're going to update it to x prime, and to go one step, we say it's a epsilon times a u, where u now represents the direction of the step, and epsilon is still the step size. U now is the direction of update. Yeah, being direction only, this vector we force it to have a norm of 1. Okay, a unit norm vector, just to represent the direction, not the step size. Yeah, so therefore we have separated these two things. Yes.
So is the x here like the augmented x?
Oh, it doesn't matter. As I said, for this hour, forget about machine learning. Yeah, we're just saying that we have a function to optimize with the argument x, whatever the x may be. Yeah, so it's just an n-dimensional vector. Yeah. Later, it's going to be the augmented one, of course, because our E in is defined, the x is augmented. Yeah. Actually, we are not optimizing x in E in. In E in, actually, we optimize w. Okay, so the augmented w will be the x here in that case, of course. Yeah. Now, so I want to draw a picture, so I can only draw up to n equal to 2, yeah, as an example. Yeah. So n equal to 2, I also have to draw the function itself as a surface. So I'm going to have a 3-dimensional figure, right? x1 like that, and then x2 is here. Okay. The surface f of x may be something that looks like this. Yeah. This is not very convex, so nice convex form like that. Now this is fx, it's a vector now. So in particular, 2-dimensional vector, right? So fx1, fx2, right? fx1 and 2, x1, x2. Yeah. Okay. Just to indicate that this is a 3-dimensional surface, I'm going to draw a circle like that. Yeah. Okay. Optimum point, of course, is at the bottom right here. Yeah. And the this is a 2-dimensional function, so this 2-dimensional plane at the bottom is the 2-dimensional x bar, right? So correspondingly, I can in fact draw the projection of this circle. Let me project this 3-dimensional surface to something that's like this. Okay, is it clear what I'm drawing here? Yeah, you have a bowl shape, yeah, 3-dimensional surface, and then this is the projection of the surface. Yeah, okay, so projection of that rim of the bowl is down here. Let's say, yeah. So let's say our current location is x. Let's say x is here. Let me use blue maybe. This point is f of x. Yeah? Of course, it corresponds to a point in the space here, which is right there. This is your x. Yeah? You are here, and the value of that point is there for the function, right? F of x. Yeah? Your goal is to find the next x. Let's say it's x prime that you want to find. You want to jump there. So this vector will be your epsilon times u, right? That's your update vector. You use a little update, you go from here to there, right? And then you say, well, where is the value of this point? Well, maybe the value of this point is right here, f x prime, right? Yeah? So you're jumping from x to x prime as the input, and then in terms of output, you go from fx to fx prime, right? Let's say now let's not consider the step size, yeah? Epsilon, let's say for some constant step size, I want to find the right direction to go, yeah? Or find the right u, yeah? Which is u itself, remember, is a unit norm vector, just a direction. So therefore, essentially we have a range to choose from, yeah? We have maybe, this is the range to choose from, the circle, right? Where the radius of this circle is epsilon. Right? I can choose throughout this circle which direction to go. Right? Make sense? What is the right direction to go? That's our question. But what criterion do we want to use when we say we choose the direction to go? What criterion we want to use? Well, one good one is a greedy idea, a greedy method, right? To say that I want to go as low as I can on the surface. Yeah? So I want to go a direction that's allow me to drop this f prime as much as I can. Or another way to say that the difference between fx and fx prime is the maximized. Yeah? But they're the same thing. So choose the direction to, let's say, minimize fx prime. Yeah, but in a small step. Yeah. In a small step, epsilon. Right now we don't talk about how to design epsilon yet. Yeah, just say we know the epsilon now. We just need to decide the direction. Okay. So in order to minimize this f prime, we have to yes.
Sorry, I know we're not like talking about AI, but like x here is not inputs, right? It's more like the weights.
That's right. Yeah, x here would be the weights later. Yeah. We want to optimize the weights. Right. So we want to minimize fx prime. So let's write down what fx prime is. It is f of x plus epsilon of u. Yeah. And we want to pick the u to minimize this one. How do we pick the right u to minimize this? Yeah. That's the question, right? Not easy because this function could be very complicated, right? How do we know what u to pick? Well, here we have, if you remember, there's a important concept that we have learned from calculus called the Taylor series expansion that can help us break down a function like this. Right? So let's see. Taylor series expansion. That says, well, starting from the point x, if I just go a small step forward, yeah, then this will be a sum of the linear terms, second order terms, third order terms, and so on and so forth, right? Yeah, we can rewrite this any function, well, any regular function into a polynomial form. It's just that now we extend this, we have to write this for a high dimensional function, so it's a bit more complicated. I don't know whether you have seen this in your linear algebra course. Yeah, so this one you still have epsilon u transpose and then the derivative, yeah, the gradient. This is the first order term, yeah, and then you have the higher order terms. So just as a reminder, in the I don't have it here. Oh. Okay, but anyway, just imagine what you did with your one-dimensional functions. Yeah, all that we do is change this to a derivative. That's all, right? And then the other terms are the higher order terms. So suppose our step size is small, yeah, epsilon is small, then all of the higher order terms we can just say group them together and say they are negligible. Yeah. Small o of epsilon square. Yeah, so negligible. Because we just want to go a small step size. This, if you want to be more careful, this is actually epsilon times the norm of u square. Yeah, but norm of u is 1, right? So it goes away. As a reminder, this gradient again is just a collection of derivatives, right? Derivative of f, partial derivative with respect to x1, partial derivative with respect to x n-dimensional, yeah, xn. Yeah, like that. So you have inner power. Basically, the u, each element of u will serve as the weight for the particular direction. Yeah, x1 or x2 or xn direction. That's all, yeah, so weighted sum of those different directions. Yeah, in some sense. Yeah. So Now we have to, given that the second term is, the third term is negligible, the first term is already given. Now we just need to minimize the middle one, yeah, this inner product. So we want to find u to minimize the inner product. Right? That's all that we need to do. Okay. How do I minimize an inner product? Yeah. So now we have to go back to your linear algebra course. What is the inner product in terms of two vectors? What does it mean? So that we know how to minimize it. Suppose I have a u vector. I can't. My pen does not work. Hold on. V like that. U vector, V vector. Inner product gives you what? Yeah, the projection and then multiplying one of them, right? Yeah, the product of one multiplying the projection of the other. Yeah, so if there's an angle here theta, then this thing turns out to be u, one of them multiplying V, and then cosine theta. That serves as a projection, if you will, like that. Okay. How do we minimize this though? Yeah, how do we minimize this u norm times v norm times cosine theta? What is the worst case that we can have? Best case to minimize it. So the smallest. What is the case that we have? Perpendicular? Are you sure? When is perpendicular, cosine will be 0, right? Is cosine equal to 0 the worst case? Huh? Huh? 90 degrees is perpendicular. See? 90 degrees is 0 degrees. No, 0 degrees, cosine of 0 is 1. That's actually the maximum case. What is the minimum case? Come on. We have 180, yeah, minus 1, right? So this is greater than or equal to negative of the norms. Yeah. And then the equality when the cosine theta is negative 1. In other words, theta is 180 degrees. Yeah. Cosine is always between minus 1 and 1. So if you can get to 100 degrees, get to minus 1, then you have the minimum of the inner product. Okay. In a way, also, you think it's inner product can be used to represent the correlation between the two vectors. Yeah. If the angle is 0, that means that they are overlapping, so the correlation is highest. Yeah. And then the correlation is minimum when they are opposite direction. Yeah. Okay. So therefore, we know that the optimal u should be the negative of the gradient, right? Because we want to minimize this product. But we also know that our u has unit norm, yeah? So we still have to normalize this so that we have unit norm. So we have to divide it by the norm of the gradient, yeah? So this is the optimal solution for the direction. Exactly opposite the gradient. From this, you immediately know that if the opposite direction of the gradient is the steepest descent, then the gradient direction would be the steepest ascent, right? It's the maximum, the best way to go up if you want to go up. Yeah. So from the analysis above, we see that, in fact, the gradient is the steepest ascent direction. In the direction where fx increases the best, has maximum ascent. Okay. Now, you might have seen this already as a conclusion, but what we have done just now is the proof that it has the maximum ascent direction. Yeah. So this is by the analysis above. Okay. And secondly, if you observe what we have, then what we're doing is what? We want to move in this direction, epsilon times u, right? U star is of that form. So now in that case, epsilon u star will be equal to minus epsilon. I'll write this here in front, like that. And then times the, right? So very often, we just take this whole thing in front without the negative sign as the new epsilon. Yeah? Basically, we merge the norm of the gradient inside together with epsilon. Yeah? So the magnitude of the gradient can be absorbed, and we usually do it, yeah, into epsilon. So that we have a cleaner form to just say a constant factor multiplying the opposite direction of the gradient. Okay. We have a bit more to say about that point, okay? But before that, let's write down the gradient descent algorithm. But first of all, any questions about everything so far? Yes? How do I get U star? Right. We know that to minimize this, U and V have to be in opposite directions. Right? 180 degrees means that in opposite directions. So therefore, when I want to minimize U times the gradient, then U have to have the opposite direction of the gradient. So it's the negative of the gradient. So that's how we get negative gradient. And then I want to normalize it U because this U only represents a direction. So it has to have a unit norm. The norm has to be equal to 1. That's why I have to divide this so that this whole thing, the norm is 1.
When you rearrange the equation, like, don't you get like the norm on top and the gradient at the bottom?
Arrange the equation up? What do you mean?
Yeah, like you just.
No. I want to say you have calculated norm of U. Calculate norm of U, then the norm of this whole thing, right? Norm of this whole thing is just equal to the norm of this one divided by itself. Yeah? So it's just 1, right? Therefore, by doing this, we have normalized U star so that U star has norm of 1 as required. You don't look very convinced, but maybe we can talk after class. Yes?
How do we absorb the gradient of f of x into epsilon if it's not a constant value?
Oh yeah, remember epsilon, in general we use epsilon t anyways, right? It's changing over time anyways. Yeah. So you can just say, well, I don't care, just ignore that this part. I just design whatever epsilon I want. It's still okay. Yeah. Very often this kind of epsilon is done by a lot of intuition and a lot of guesses anyways. Yeah. But we have a bit more to say about this point, okay, after we write down the algorithm. So we have initialization, of course. Well, initialize maybe. Just initialize x0, and then and this, of course, typically at random. It doesn't matter where you are, especially you have a convex function. Doesn't matter where your starting point is; it's guaranteed to converge to the optimal point. So just pick one at random, and then you go through the steps, 0, 1, 2, and so on, yeah, until convergence, of course. First, you compute the gradient at that point. Let's call it g of t, the gradient of fx at time t. Now, this way of writing is a bit redundant, okay, but we do this for a reason, because later when we have a more general version of this, more complicated versions of gradient descent, we'll have to break down these steps. That's why we write down all of the details. Yeah. We're going to select a direction, VT, that is the negative of GT, negative direction. And then we update t plus 1 from xt by just multiplying some epsilon t, some step size, multiplying vt. Yeah, and then we go back to step 1 unless you're close enough to the optimum. Yeah. So until stopping criteria, usually there could be multiple actually, reached. Okay. One thing to know is that, well, this conditions for stopping, of course, when do we stop? How do you know that you are close to the optimal point? Because you don't know what the optimal point is, right? How do you know that you're close? The change is small. What do you mean the change is small? Well, the change is small only tells you that your algorithm converges to some point. You will not necessarily know that it's converged to a good point, right? So how do we know that we're close to optimal point? Remember the one-dimensional case? When the loss is small, well, no, there's a better way, yeah? Again, that only tells you that you are converging. That's not tells you that you're converging to an optimal point.
When the gradient is 0?
Yeah, when the gradient is close to 0, right? Just think about the one-dimensional case. You want the slope to be 0, right? It's the same thing here when you extend to the high-dimensional space. So very often people look at this, at least as one of the criteria. It's let's say it's just reasonable, okay? Things get more complicated in say, non-convex cases. We'll have some discussion about that later. Oh, I should say, bar like that, it's a vector, right? And usually you just look at the norm of this gradient, yeah? If the norm is close to 0, then we know that the vector itself is close to 0. Yeah. Second point is that it's on t. It's a time varying. It's a well-known name for it called the learning rate. When you apply this method to machine learning, yeah. Normally it's called the step size, but we also call it the learning rate. It is learning rate in the sense that you're multiplying this epsilon to the gradient. Where do you get the gradient from? Well, we'll see next time when we go back to machine learning, that this gradient you learn from your data. Okay? So you learn from the gradient from the data, and then you say, how much do I want to account for this new knowledge from my data? Yeah? And the weight epsilon is how much you account for that new knowledge. Okay? So therefore, this is called the learning rate. Yeah? You get new knowledge from the data to get the gradient, and then you update your current decision x. Right? So this learning rate controls how much of the new knowledge you want to use. Right? Yeah? So it makes sense to call it the learning rate of learning. Higher value, the more learning you want to do, but sometimes it can lead to instability. You can jump around the optimal point, it doesn't converge, right? So you don't want to, when you're getting to the close to optimal point, you don't want to learn too drastically. Now, another interesting point here is that very often in practical implementation, in particular, if you look at the default PyTorch implementation of this for training neural networks, they use a constant learning rate because it's very hard to decide if you use a time-varying learning rate, exactly what function to use. They say, well, too complicated, give up, let me just use a constant number. So now you wonder, well, what happens in that case when you have a constant epsilon in this form, right? In this form of the epsilon. But notice that this epsilon already absorbed the norm of the gradient, right? This is not our constant step size as before anymore. This already absorbed the norm. So even when this epsilon is constant, things are changing. Okay? So if we have a constant learning rate, epsilon is used. So epsilon t is always equal to epsilon, right? Okay. So that means we have epsilon times Vt, right? That's what we use to update. Yeah. So this, let's write it out. Vt is simply that negative gradient. Yeah. What is this equal to? Well, remember what is our U star? U star is this guy, right? So I can write it out again. Put this back. It's epsilon times the norm of the gradient times U star. Yeah, that's just by our definition of U star from before, right? Yeah. So remember, the U is a unit norm vector, only represents the direction. Yeah. So anything in front of it will be your real step size in that direction, right? So you notice that now your step size actually includes the norm of the gradient. Yeah. Okay. So when you program your code in this way, and specifically that's implemented in PyTorch and well, almost all of the other libraries that do machine learning. They always do it this way. So in fact, when you use the constant learning rate, your actual step size is diminishing as you get close to the optimal point. Yeah? So as we discussed before, this is a good thing, right? This is a good thing. Yeah? The actual step size is getting smaller and smaller. So it's safe to actually set a constant step size in this sense if you just want to make things easy. Yeah? Just use the default setting of these libraries. That's perfectly fine, turns out. So it diminishes as ST gets close to the optimal point. Yeah? Okay. But of course, if you want to be more fancy, especially when your optimization problem, your learning problem is to be more challenging, you might want to have your hand-tuned step size, epsilon t, yeah, to make it converge better to a better solution, especially when the problem is non-convex and so on, and you have some knowledge about the system. Yeah. But usually constant learning rate works okay. All right, so much for now. Everything's okay. I'll see you next week.